The year 1874 marks a pivotal moment in the history of mathematics, specifically with Georg Cantor's publication on a question concerning the countability of all real numbers. This seminal work, appearing in Crell's journal, shattered prevailing assumptions about the nature of infinity and laid the groundwork for the modern field of set theory. To fully appreciate the significance of Cantor's contribution, we must first understand the intellectual landscape from which it sprang and the mathematical questions that then occupied the minds of leading thinkers. Prior to Cantor's work, the prevailing view of infinity was largely influenced by the philosophical and mathematical traditions of the ancient Greeks. Euclid, for example, had established the existence of infinitely many prime numbers but lacked a framework for comparing different sizes of infinity. While mathematicians understood that a set of natural numbers, often denoted by the letter n, was infinite, they generally assumed all infinities were equivalent. This view stemmed from the intuitive belief that infinity was a singular concept, a limitless expanse beyond human comprehension, rather than a concept that could be analysed and rigorously explored mathematically. Figures like Bernard Bolzano, though he made early contributions, faced opposition in his time for exploring similar notions. Bolzano, in his Paradoxes of the Infinite, had already begun to grapple with the idea of different kinds of infinity, noting that infinite sets could have infinite subsets. However, his work, although prescient, was largely ignored or dismissed during his lifetime. Thus, Cantor entered largely unprepared for his revolutionary eye. Cantor's primary motivation stemmed from an investigation into the foundations of analysis, specifically concerning the concept of continuity. The prevailing understanding, largely based on the work of mathematicians such as Cauchy and Weierstrass, saw the real numbers as forming a continuous line, and that every point on the line was associated with a real number. He wanted to understand if the set of all real numbers could be put into one-to-one correspondence with the set of natural numbers. If this were possible, it would imply that the real numbers were, in a sense, countable, meaning they could be enumerated. This question formed the core of the inquiry Cantor undertook. The core of Cantor's 1874 paper revolves around a proof by contradiction. His central argument, known as Cantor's diagonal argument, demonstrated that the set of real numbers is uncountable. He showed that there exists no one-to-one correspondence between the natural numbers and the real numbers. He proved that the real numbers within the interval between 0 and 1, specifically, cannot be placed in a one-to-one correspondence with a natural Cantor began by assuming that a one-to-one correspondence existed. He supposed that all real numbers between 0 and 1 could be enumerated in a list, each number presented as an infinite decimal expansion. Then, he constructed a new real number that differed from each number in the list in at least one decimal place. This new number, by construction, could not be in the original list, thereby contradicting the initial assumption that all real numbers could be listed. To illustrate this, suppose we have a purported list of real numbers between 0 and 1, represented as decimals: number 1 0 pointer sub 1 1, a sub 1 2, a sub 1 3, number 2 0 pointer sub 2 1, a sub 2 2, a sub 2 3, number 3 0 pointer sub 3 1, a sub 3 2, a sub 3 3, and so forth. Where sub I, j represents the jth digit of the ith number in the list. Cantor then constructed a real number, let us call it b, between 0 and 1, defined by the following. The first digit of b is different from a sub 1, 1. The second digit of b is different from a sub 2, 2. The third digit of b is different from a sub 3. This implies the nth digit of b is different from a sub n. N for all n. The construction of the number b ensures that it differs from every number on the initial list in at least one decimal place. Therefore, b is not a real number, if the original supposition is true. This self-contradiction proves there is no one-to-one correspondence, or the set is uncountable. The implications of Cantor's proof were far-reaching. First, it showed that there are different sizes of infinity. The set of natural numbers, the set of integers, and the set of rational numbers are all countably infinite. However, the set of real numbers is uncountably infinite, demonstrating an infinity of a higher order. This was a radical departure from established mathematical intuition. The established understanding of infinity was fundamentally altered. Cantor's work thus introduced a hierarchy of infinities, a hierarchy that defied the common-sense notion of a singular infinity. The immediate impact of Cantor's work, however, was not universally positive. The implications of his work were so radical that they generated a mixture of enthusiasm and skepticism from his contemporaries. The paper was initially met with resistance and criticism from prominent mathematicians, including Leopold Kronecker, who held strong convictions about the constructive nature of mathematics and was skeptical of the concept of actual infinity. Kronecker believed that mathematical objects should be constructed rather than postulated, a viewpoint that contrasted with Cantor's acceptance of infinitely large sets. Kroneker's criticisms, along with others, were deeply rooted in the broader philosophical debates surrounding the foundations of mathematics. Despite these initial reservations, Cantor's work began to gain traction within the mathematical community. During the next few years, Cantor engaged in an ongoing exchange of letters with other mathematicians, including Richard Dedekind, who provided support and encouragement. Dedekind's own work on the real numbers, particularly his development of Dedekind cuts, provided crucial support for Cantor's ideas. Dedekind understood the profound nature and the import of Cantor's set theory. The work of Dedekind, in turn, provided Cantor with the tools to refine and expand upon the subsequent development of Cantor's set theory, particularly his work on ordinal numbers, demonstrates the evolution of his thinking and the ever-expanding depths of set theory. Ordinal numbers, a generalization of natural numbers, allowed Cantor to define different sizes of infinity and to explore the transfinite numbers, providing a consistent method to classify different levels of infinity. This was a seminal development, going far beyond the initial findings of his 1874. The development of ordinal numbers and transfinite arithmetic provided a framework for consistently dealing with the different infinities that he had discovered. Cantor's work, although revolutionary, was not without its challenges. Throughout his life, he faced personal struggles and professional isolation. Partly because of the contentious nature of his ideas, he wrestled with periods of depression and mental illness, a burden that further compounded his difficulties. He found that his ideas were difficult for many mathematicians to accept, which led to a sense of intellectual isolation, further exacerbating his personal struggles. The legacy of Cantor's 1874 paper is immeasurable. It revolutionized the foundations of mathematics and paved the way for the development of modern set theory, which is now a fundamental concept in almost every branch of mathematics. Cantor's ideas have had a profound influence on the development of topology, real analysis, and mathematical logic. In topology, for instance, Cantor's work provides a framework for understanding the properties of sets, including the idea of cardinality. The concept of a continuum, closely related to the real numbers, became a central object of study in topology. The notion of cardinality, which Cantor first rigorously defined, became critical for classifying topological spaces based on their set. In real analysis, Cantor's work led to a deeper understanding of the structure of the real number system and the behavior of functions. The concepts of countability and uncountability became essential tools for studying the convergence and divergence of sequences and series, which are fundamental in the study of calculus and more advanced analysis. Cantor's work aided in clarifying the complexities of functions on an interval. Cantor's work also had a significant impact on the development of mathematical logic and the foundations of mathematics. It provided the impetus for investigations into the axiomatic foundations of set theory and the development of formal systems for describing mathematical objects. His foundational work on sets and the infinite directly influenced the development of Zermelo-Freenkel set theory, the standard axiomatic system for set theory now used by mathematicians. Cantor's work also influenced the works of Hilbert, Russell, and Gödel, each of whom built upon his foundational ideas. David Hilbert, for example, recognized the importance of Cantor's work and incorporated set theory into his program to formalize all of mathematics. This program, known as Hilbert's program, sought to provide a complete and consistent axiomatic basis for all of mathematics. While the program itself was later shown to be unattainable, Hilbert's embrace of Cantor helped to legitimize and popularize set theory within the broader mathematical community. Bertrand Russell, in collaboration with Alfred North Whitehead, undertook a monumental effort to ground mathematics in logic. Their Principia Mathematica, published in the early 20th century, aimed to derive all of mathematics from a set of axioms and logical rules. Russell and Whitehead relied heavily on the concepts and techniques developed by Cantor. The publication of Principia Mathematica showcased the importance of Cantor's work in attempting to formalize mathematics and establish a rigorous foundation for its logic. Kurt Gödel's incompleteness theorems, which shook the very foundations of mathematics, were also, in a sense, built on Cantor's work. Gödel demonstrated that any sufficiently complex formal system, including those based on set theory, will contain statements that are true but cannot be proven within the system. This result, while not directly related to set theory, built upon the same conceptual groundwork established by Cantor, the impossibility of a complete and consistent axiomatic system, a concept that has a parallel in Cantor's demonstration of multiple infinities, shows the limits of formal systems. The impact of Cantor's 1874 paper has extended beyond mathematics. It stimulated philosophical debates about the nature of infinity, the foundations of mathematics, and the limits of human knowledge. His ideas also influenced broader fields like computer science, where the concept of countability and uncountability play essential roles. Furthermore, the concepts of infinity, cardinality, and transfinite numbers became central to debates about the nature of reality. In conclusion, Georg Cantor's 1874 paper on a question concerning the countability of all real numbers stands as a landmark achievement in the history of mathematics. It not only dismantled established notions about infinity, but also laid the groundwork for the modern edifice of set theory. The paper's impact on the development of mathematics, its widespread influence, and its enduring legacy across various disciplines are a testament to the power of Cantor's insights. His work continues to inspire mathematicians, philosophers, and scientists alike, shaping our fundamental understanding of the universe. His revolutionary findings reshaped mathematics and our very conception of infinity.